Okay, I guess it's past time to start back up, but let's start back up before it gets any too much later. Let's see, 150, not too bad. I only cut it by 45 minutes. So, I went, during the break, I went and I looked at to see what we had left to cover, and we don't actually have that much more. So we might actually get out of here before, but it's, I think about another hour. I'll probably get out of here by 3 or 3:30, is what I'm thinking, if you're trying to plan rides and stuff like that. So let's see what we got going on here. During the break, I also uploaded so I can show you what the videos look like, and there's a new link here. It says video lectures, actually, on the website. This is in the Software Engineering 1 weekend section. So if you click on video lectures, you see 521. I broke it up into 2, actually, because we had a break. So I'll break them up, and each one of them is like about a couple hours each. So I like to do like 1 to 2 hours. Even though it's YouTube, I can do more than 10 minutes on my account. So what you'll see in the next coming weeks, starting next week, is Lecture 1, Lecture 2, which will be for the weekday class. I'm going to put them in the same spot. So we'll see the weekend and the weekday together, because what you might want to do between now and, well, the first couple of the weekday ones are going to be the same, because we're going to cover what we've covered up to through today. I'm going to do 2 more lectures for you. And then, depending upon the timing of this course, it looks like we're going to finish earlier than the weekday. So it may or may not necessarily be of any use to you. But if you want to, you have the option of looking at each one of the different lectures from both sections. So I thought I'd point that out to new people, which you guys are left are the new people. So most of you are. So you at least know where to find the videos. So
the weekday class hasn't started yet?
No, it doesn't start till tomorrow. Oh no, Monday. Monday is when the weekday classes start, and this one is going to be on Wednesday. So in fact, let me just double check that real quick, because I'm doing this from memory. See, that's why I put the dates here, so I remember myself. Software engineering meets on Wednesdays at 11 o'clock a.m. So if any of you do want to attend that section of the course, you may if you're local. But that one doesn't start till this coming Wednesday. So this class is now ahead, which is why I said I don't know if those videos are going to be of any use to you now that I think about it, because we probably were going to get, by the next class session, which is in less than a month, they may not even be caught up with us by then. I don't know. So usually it's the other way around. So any other questions you guys thought of during our lunch break? Okay. So let's go through a couple lectures. I'm going to cover Lecture 3 and Lecture 4. And let's see, here's Lecture 3. Let me just start it here. There we go. All right, Lecture 3 is on requirements and design. I just gave you the format for the requirements document, page 25 of the course notes. Download the course notes, download the syllabus. You guys have a lot to do in the next 20 days or so. Because we come back here, like, I thought it was a month, but it's a little less than I just realized. So I'm going to talk about requirements as well and lead that into analysis and design. So we're moving right ahead. So what we've done is we've gone to about 3 weeks already worth of class material. So this is like week 4. So we are into the requirements and design as a principle. This is a little review. Requirements should state what the system's supposed to do. Remember that the design states how we're going to do it. So we're looking at the what and the how. In practice, requirements and design are supposed to be inseparable. And that's where that traceability concept comes into play, because they're both the same thing. They're just different abstractions. And remember I talked about software engineering as being there's different levels of abstraction associated with it. One of those kind of phenomena that occurs when you're doing requirements and we're doing a design. It's the same thing, but it's just different focuses. You've got the what and the how that separate it out. Requirements document is the official statement, if you remember. Just refresh your memory a little bit about what the system developers want to build in terms of the what. It should contain a definition and a specification in the real world. We're just going to do the definition. But theoretically, we should have a specification as well that goes along with that. And it's not a design document, it's just what rather than the how. And when we start doing the what, we basically have got our wish list together. And then we start putting the wish list into action. And we start creating the how. And here's the real IEEE Standard looking document. And this is where those 1.1, 2.1, 3. That's the numbering system. Other ones use more of an A, B, C, A.1. They use alpha and numeric. This one actually follows numeric. And if we were looking at a true IEEE standard, we'd see categories that were specific, that were required to have. But as I mentioned before, you can use any format you want, any sections you want in that. And we looked at before the different types of requirements. There's a little review in this lecture right in the beginning. So we got functional, non-functional. We can even say user requirements. I don't like the template. In fact, maybe I should modify it one of these days. I like it because it was actually a real requirements document. So page 25, that's actually a real piece of work. But it's really bad, actually, because it says general requirements. What is a general requirement these days? It doesn't say anything. It's probably better to break it out into user interface requirements, database requirements, network requirements, operating system requirements, something more descriptive outside of the word general. But here we have user requirements on the bottom, non-functional, functional. These are just some sort of different types. So after we get done saying what the system's going to do, we start working on the design document. In the real world, there is no analysis document, as I originally stated. Analysis document's made up as an assignment for you. Instead, the design team is doing the behind-the-scenes design work. They're putting together the design and they're doing analysis. So in the old days, they used to call it systems analysis and design. Or actually, it was abbreviated SAD, but that's a negative. So, people want to have happy feelings. They don't want to have sad feelings about their software. So systems analysis and design. Nobody ever says SAD anymore. They just say analysis, design, and they leave out the word system usually. But that is what they used to call structured analysis as well, because it's like a methodology you're following to do structured analysis. But that's on one side of the fence. The other side of the fence, we have a brand new breed of object-oriented analysis. These are frameworks. So we started out with structural system way long before object orientation came along. And we have object-oriented analysis and design. Brand new, different way of thinking, same concept. So all of this analysis that you're doing is basically understanding the system. So you're mapping out, you're creating charts, symbols, graphs, you're listing out information, you're presenting the system from a couple of different viewpoints. And that's what the analysis stage is all about. I'm not going to bore you with analysis at this point. I'm going to overly analyze the entire process, and then the next time we meet, we'll get into all of the different entity relationship, data flow, UML, all the different diagramming. So next time we meet up, it'll be all about diagramming and all about things you have to be doing. We'll be studying the design, essentially, next time. But to give you the overview of it, what we're looking at is the how. In order to put the how together, we have to understand the system. In order to understand the system, we got to model the system. And the modeling is a very abstract kind of concept. And you say a model, a picture says 1,000 words. So you draw a context model, and you can easily see how the picture works together versus reading about 10 pages of descriptions on it. So software engineers, they like to put models together. And then we have different stages in the design analysis that we start through. And most of it's simplified these days because it depends on the methodology you're following. We're going to do a little bit of both. We're going to do systems analysis and design, and we're also going to do object-oriented analysis because those actually can be done together. In a real-world scenario, if you were building an object-oriented program, you're probably just going to do object-oriented analysis. You're not going to bother with structured analysis. Why? You can do everything that structured analysis does with object-oriented design. But we don't know if we're building an object-oriented system or not, so you do both. And so most likely in the real world, though, you're not really going to do both. So in terms of this particular example that you're looking at, we have a university admissions system that we're going to analyze. And this is just kind of an overview of the stages that goes into the design analysis, which is your next step. So we have applicants, we have university administration, we have computing staff, we have all of these different entities. Object-oriented people call them objects. Systems analysis and design calls them entities. So that's where that entity word comes from. Actually, there's nothing new. Are you guys familiar with object-oriented design? Programming? Object-oriented programming? Oh, all of you, except for you in the back. What field do you come from? What? Business. Oh, congratulations. You've made the jump. All right, well, that's good. That's actually good for you in software engineering. Because this is really a business kind of topic area. But anyway, in object-oriented analysis and design, usually they teach object-oriented programming. They rarely actually teach design philosophies. Because then you have to get into analysis. And nobody likes analysis. It's not programming. It's just a way of breaking out the system into components. So think of these as different objects. Object is conceptual. Object is person, place, or thing. Objects are the same in programming as they are in design. So step number one, we organize the requirements. We gather a list of the requirements and create a requirements document. We've done that. Well, let's assume we've done that because we're in week 4 already. So we've already put that together. And now we're going to perform what's called design analysis. And we're going to create an analysis document, which is the first draft of our design document. So we're really working on the design at this point. We take the requirements and we perform what's called design analysis in order to create the analysis and the design document. And here's our major set of common modeling techniques. So it's easy to say you're going to build a product and create assembly line and figure out all the parts that are going into this product and plan everything out in terms of its components. That's easy to plan. When you take a set of requirements and you're going to plan the development and the construction of the system, a little bit more complex. Before we can actually do the planning, which is the design, we have to do the analysis, which is kind of a separate state nobody ever looks at in any other field. And as I mentioned before, analysis usually is represented by the composition of these models. And the models fall into these kind of general concepts. And I'm going to explain in about 10 minutes' time the difference between systems analysis and design and object orientation in a quick and easy way of kind of remembering it. Because it actually plays into what it is we're analyzing and what it is we're actually formulating into the design. Procedural models, data-centric models, object-oriented models, and formal models are the categories. So a long, long time ago, history lesson number 1, anything before object orientation, we had data and we had processes. And that's what we modeled. We took the data and that turned into, it came from an entity relationship diagram, actually. And we converted that into data in the database schematic. And if you take my database class, we just taught it, Oracle class, for new people, you'll have to wait. Actually, it's being taught. I'm not quite sure what the teacher's going to do with that one, but the other guy. But anyway, long story short, we create a model for the data. And that model, the entity relationship diagram, and we're going to cover this next session, turns into the database design. And then at the same time, we look at processes. We look at data flow diagrams, which you'd think would be used, the data flow diagram, you'd think would be used for the database, but it's not. It actually looks at the processing of the data in terms of the flow, how the data works through the system, which is processing, not really data. It's just data components. Both the diagrams actually work together, but they're modeled separately, 2 separate diagrams. Object orientation, put them both together. So we have all of the object-oriented models have data and processing together. We end up with a class diagram. We end up with use case scenarios. We end up with sequence diagrams, transformation diagrams. Everything has everything all in one basket, which is really the difference between systems analysis and design and object orientation. And some other models out there is how they're separating the differences between the data and the processing. And if you could break a system down, decompose it, which they refer to, well, there's a couple of decomposition methods. One of them used in the traditional systems analysis and design approach is called functional decomposition. So step number 1 in their analysis is you take the system and you decompose it into its functional units. You say, what kind of functions do we have? And you almost look at it from a user interface point of view. You say it's an accounting program. We have accounts payable, accounts receivable, reports, and all this functionality or features of the system that you can divide out. That's functional decomposition. And then once you functionally decompose the system, then you take and create a data flow diagram, entity relationship diagram to look at the data and the processing. You have to do one of each. They're separated out. And then once you understand, then you can come up with process descriptions. Those turn into your algorithms. And then you look at the entity relationship. That turns into your database, your data storage. Because all systems store data these days. And all systems do processing on the data. And then you can look at other concepts that are associated with the running of this particular system. And then lo and behold, you have all the pieces. And you put the pieces together, and that turns into your design document, which is the analysis process. In object-oriented analysis, you're really doing the same thing, except for you're using what's called UML. You guys used that before? Unified Modeling Language? It's just another way of, for you in the back, it's just another way of decomposing the system into models and representing the components. And in object orientation, we're looking at objects. And objects are implemented in the form of a class. So we have class diagrams, sequence diagrams, inheritance diagrams, all these different things that are associated with the object orientation. And I'm going to be talking about object orientation in the next class meeting as well. The other two, the data-centric process models, formal models. Actually, I already talked about data. These two up above, actually it's easier for me to go like this. These two up above are systems analysis and design approaches. Object-oriented models are breed of their own. Formal models, that describes everything. These are all what you would call formal models. But formal models also encompass things that are outside of the system. So we have contextual diagrams and component diagrams. So a contextual diagram shows the system in the context for which it's operating. Oh, thank you. Great. We'll get through the next lecture. Speedy now. So in a contextual diagram, we're looking at a framework. It's not really the system we're modeling, it's the environment that the system is sitting inside of, which would be a breed of formal models that doesn't fall into any of those categories. So let's take a look at the categories a little bit more in detail in terms of what it is we're looking at. Hot coffee. All right, so procedural models. Anyone actually grow up in the time period in which, well, anyone actually learn BASIC? I know I'm really dating myself. Line numbers, go-to statements, QBasic, C. Yes, C. You missed this entire generation of flowcharting. Back when we had BASIC, actually some teachers still taught it was C. ANSI C, just standard non-object-oriented version of it, where you took and you created a flow. Before you wrote any source code, you took a description of the problem and you wrote a flow chart, and then you took the flow chart and there you had your flow control for the program, had all your yes and no routing, your if-then statements, everything you needed was right there, and you just translated that into the source code. That's what this analysis is all about. But it started way before C. And then it faded out with C. After C, nobody used it anymore. I don't know why. Probably because it doesn't lend itself well to modern programming languages. You can't do that anymore. Now you have to have object models. Anyone ever heard of Object View Controller? Everyone's heard of it. Nobody really knows what it is. It's kind of like flowcharting, but it's for object orientation, where you've got the control unit, you've got the view, the object interaction, and the object hierarchy, and you put all those pieces together and you got model view controller. And it's just a methodology similar to flowcharting. It's just nothing more than terminology in terms of the design, that putting the pieces of the components together so you've got a workable system. There's a flowchart for the university admission system. And the symbols, don't worry about the symbols, you don't have to do it for this class. It's just memory road. History lesson, number 1. So we have pieces going together. The form was received, is it new? Then update the database. Or if it's false, update. If it's new, put the record in. Common flow that would happen. And then we have this termination button that says evaluate that turns into a process. So we took it and we looked at the flow, and then we evaluated it, and then we turned it into a data problem from a process flow. So this is only looking at the processing. So you can kind of sort of see if we're looking at this model approach, we're looking at the procedure, the processes. It's actually quite a logical flow that we're diagramming. We still do this. We don't do this right to source code anymore, but we still use the technique, but it's to model the system. So we could put together a process model. We could. We're not going to have to do it for the project. I'll tell you which ones I need to do for the project, but it's outdated. But it's not bad. It had its point in time. And then for the pseudocode, you guys remember pseudocode? It's either as a beginner programmer you had to write pseudocode, and then as a graduate student writing a dissertation you have to write pseudocode. That's about the only 2 times in your life that you actually have to write pseudocode. Everything else you might as well just write the source code, right? Unless you have to explain it to somebody, you just write it for them, essentially. But pseudocode was supposed to be like an English-like language. That's high level. You know, that it's supposed to go through the entire program. That's getting to the point where you might as well just write the source code. But it was supposed to be language independent. Now we have the data flow. We're still looking at a procedural model. But this is the flip side. This is the data portion of it. This we still use the data flow diagrams. And they look like that. So we've got an application that comes in. And these little circles at the end are sort of data points. Application. So applicant comes in, we have an application form, it's received, and then we have a completed form that goes to evaluation. And it's kind of flowing this way, but essentially the data can be read in any direction. It's kind of like how that previous flowchart, it depends on where you start and kind of go through. But this is really showing the data transformation, and these are process bubbles. What happens when you evaluate happens inside of this process. Receiving the application, there's a process for that as well. And then here's a more elaborate one. It puts some more pieces together. And what ends up happening is you start decomposing the system into these data flow diagrams, these entity relationship ones, these, well, I haven't seen that one yet, data flow charts and stuff. And this is what's called the analysis stage. You're creating all this stuff that you're going to use in the design. You have to express your ideas in terms of your decomposition and all the modules and things that you've created. And most people come up with what's called module designs these days. Even if you're not doing an object-oriented program, you have modules. Because that promotes reuse, promotes flexibility in the design, efficiency in the design, stuff like that. So, good qualities in the design. So there's another example of process completed for the application stage. This one was the assembling the application. This one was the university admissions. So that's everything. And then we have a deeper level of abstraction, looking at the assembly application and then the completed application. Really all the same system, just showing you different parts of the system. So what you end up doing is you model the non-obvious parts of the system. Maybe you can create a simple one that shows you a high-level overview. But what we have are different levels of abstraction, which is the goal of the analysis. You want to kind of look at the left side, look at the right side. It's kind of like when you analyze a car. I'm going to buy this, I don't know why I'm talking about cars today. You're going to buy this new car, or a used car. New ones are easy, it's a no-brainer. Used car, sometimes guys go kick the tires. I don't know what you kick the tires for. I think that was an old commercial or something. But you got to open up the hood, turn the engine on, see if you smell any smoke or something. Take a look at the inside. Oh, the seat's all torn up. You're analyzing it, but you're looking at the seats, you're looking at the engine, you're looking at the tires. Some people take it to a mechanic, get it checked out. So what you're doing with the software is pretty much the same thing. You're looking at the outside of it, the inside of it, the data part of it, the processing part of it, the networking part of it, how the software is going to work. When you test drive the car, you could build a prototype of the software and test drive it to see if you understand all the requirements correctly. Does it turn to the left? Does it turn to the right? It's the same thing you're doing with software. It's another way of analyzing it from a lot of different perspectives and abstractions. So we do our requirements analysis, and that turns into our system design. And they're really two separate, discrete applications. So in the requirements, we should hopefully make minimal assumptions about the system, which means keep it broad. So I remember before I said don't use Microsoft Visual C++ 6.0 Too specific. Requirements are broad. Design is specific. It's not quite as broad. It's because both the requirements definition must be consistent with computing technology and resources that are available at the time you want to implement it. So when you spec out, think about requirements, practice analysis and design are supposed to be interwoven. If your requirements are too specific, your design is impossible or infeasible. So think about the concept of buying a television set or something, because I want to change from cars. It's kind of boring. So, TV, you want to buy a TV. And you got specs about the TV. And the specs about the TV, if you were looking at today's TV markets, where they have plasma, you got what, I don't know anything about TVs, maybe that's not a good thing. LCDs. So if you said in your requirements document it has to be an LCD, or it has to be plasma, what about 10 years from now? We're probably going to have something else. Maybe we won't have either one of those two technologies, which means it's going to be impossible to buy that TV according to those requirements. But if you said it must be thin, must be a flat screen, but you didn't specify out the technology, then that requirements document survives through time, and it grows with the times, and you can actually have different implementations of that same requirement. You could upgrade in the future, but it's still the basic requirements. Must show a picture of 50 by 50 or something. It must be huge. Or maybe you want a projector. Maybe you want to go on a wall or something like that. I don't know. If you're broad, then you can actually buy it in the future. If you're too specific, it may not actually exist, which might be an issue. And it doesn't lead to very much flexibility. It's too overly constraining. So requirements in the design in terms of scenario planning. So we can create scenarios. I mentioned before we have this thing called scenarios, which can actually help you figure out what the requirements should be for the system. So you create scenarios that are descriptions of how the system is used in practice, as I mentioned before. And they're helpful for the requirements, and they're also helpful for adding detail to the requirements description, and they're also used as part of the analysis. Because when you put together your requirements, what you're trying to do is cover everything. So you actually have to do some analysis to put the requirements together. Otherwise, you're not thinking about the system.
Are we talking about use case scenarios?
Yep. Scenario planning, just use case scenario. Well, let me clarify something for you. Scenarios existed long before use cases. Scenarios are from systems analysis and design. UML calls them use cases. And that's how everyone calls everything use cases. It's kind of like the concept of the cotton swab. Yeah, no one's like, I need to go buy some cotton swabs. And they say Q-tips. Because this is a brand of cotton swabs. Use cases are a brand of scenario planning. Scenarios, use scenarios. The problem is that most people call them use cases. And when people say use cases, immediately I think of UML, object orientation. But I'm really talking about scenario planning. I make the same mistake myself. I'm really thinking about scenario planning, which is not use cases at all. It's systems analysis and design. So it was here a long time before use cases came out. But it's the same concept. Okay? Q-tips and cotton swabs. So here's a use case scenario. And this is not a use case scenario. Excuse me. This is a scenario. This is scenario planning. This has been around for years prior to object orientation. If you were to do this in an object orientation fashion, which we'll see next time, next weekend we can meet, we'll see stick figures, we'll see flows. It's just documented differently because the styling is different. It's UML, it's not structured analysis. But here we have a scenario for an ATM machine. We have a pin and a card that gets put in. Card's present, request a pin. And we have all of these, looks like a flowchart. We have all of these outcomes that occur and these other events. That we see all the time. That actually kind of replaced flowcharting. That's the UML version of sequence. We have sequence diagrams in systems analysis and design. It's a state diagram. Yeah. So by the time we get done talking about all this stuff, you'll think, UML is nothing new. In fact, object-oriented design is nothing new. Although the interesting thing is a lot of people didn't learn anything about design until they learned object-oriented analysis and design. And they went, wow. That's because they never took a structured analysis and design class. Because object-oriented made it actually seem easier in a lot of different ways. It's just another form of structured analysis with some different labels on it, is what it is. And it takes and combines data and processing together. And what they did is they just supplemented. UML has a lot of diagrams. Anybody use UML in this class? Anybody heard of you do? Rational rows?
Yeah.
Yeah? Mm-hmm. How long did it take you to learn all that stuff?
Actually, I haven't worked on it practically, but I know how it works. You know, templates, you just have to put up the requirements, and it's kind of similar to Visio.
Yeah, Visio.
Yeah.
That's another good. How many people know how to use Visio? Know everything about Visio?
No, you
How long did it take you to learn Visio? You
It's
can't.
hit and trial. I mean,
Yeah, I'm afraid of the program. I don't even open it up. I'd rather use open source tools that are like not quite as. In fact, I'm not a fan of .NET and the whole Visual Studio either. Although I have struggled with it for many years, but I hate it. It's too complicated. Rational Rows is one of the worst tools I've ever seen on the market. So is Visio. So is all this stuff because it's got the hundreds, 200 symbol sets.
but you use only 10, 15, 20.
Yeah, you use like 10 of them. Believe it or not, that's what you do with object-oriented analysis and design and UML. I can probably list off about a handful of documents, or excuse me, diagrams that people create. Everyone's heard of the object diagram. Well, okay, maybe if you haven't, don't worry about it. Object diagram, class diagrams, sequence diagrams, state diagrams, machine. Well, if you're doing a what do they call that? A state machine, where it's like an auto. It goes in a circle like a loop. State machine diagrams. I lost track. Inheritance diagrams. There's, I think I'm up to 6 or 7 at this point. I only know about 4 more, I think.
Use case diagrams.
Use case diagrams are 8 or 7.
State diagrams.
I've said that one already.
Yeah, these are pretty much.
And you know how many UML diagrams there really are? Hundreds. Hundreds.
I don't know. Yeah, but we use 6 or 7.
6 or 7 of them, yeah. And that's what we're going to look at in the class. We're only going to see about 6 or 7 of them. The ones I just mentioned actually are the ones we're going to look at. And you only have to put one of them in your design document. So you won't have to learn all of them.
So in analysis document, you have to put more diagrams. I'm just trying to understand what are the requirements.
Think of the analysis document as the first draft of your design. And by the time I'm done, actually after this lecture, we're going to go look at the analysis document. I think it's on page 46. And take a look at it. You don't have to do it for the next time. If you get the requirements done, you'll be in great shape. I'm going to preview sort of the analysis to let you know what it is we're doing, because it helps to understand it. Analysis, you're turning in an analysis document. It's really the first draft of your design document. I have 2 different formats for you. I have one for the analysis, which is nothing more than an accumulation of diagrams. So you're going to create at least one entity relationship, at least one data flow. We'll talk about it next time. 1 UML. That's about it. It's not that complicated. And you'll use those and you'll turn it into your design. And you'll supplement that with more stuff, like a test plan and stuff like that.
So are you expecting any kind of diagrams for design doc as well?
Yeah. I'll preview both of those documents for you next. So you'll see what I'm talking about. Because it's nice to know what you're getting into. You could plan ahead as well. But that's what we got here with the scenario. And then we got the introduction to the use cases. And we kind of talked ahead already, but it's part of UML. Use cases comes out of Unified Modeling Language, which we are identifying actors, and they call them actors, and they have interactions. And I don't know why they're actors instead of people, users, but everybody's an actor. You have a set of cases that describe all the possible scenarios. You can write it up graphically, or you can write it up in words. And here's what it looks like graphically. Stick figures. In fact, you see this. Usually it's a little bit more complicated. This is too easy. You're going to come up with a use case scenario diagram, that's going to simplify a huge complex kind of thing. Oh, where does the user interface with this? You know, if you've never heard of the concept of an ATM, you might not understand that the ATM withdraws money out of your bank accounts. And, you know, if let's say that ATMs never existed before. In fact, people in the beginning had a problem understanding what do you use an ATM for. In fact, a lot of people wouldn't use them for years in the United States. A lot of people would go to the bank. Oh, I could do that from the ATM. So then, you know, if they just had use case diagrams put together for it, then they'd understand, oh, look, you can transfer funds between accounts. Look, you could put a stop payment on a check. Look, you could do this. You could do all of it through the ATM. But now we already know what ATMs do. So. And here is also another use case. Getting a little bit more complicated because we've combined that with some sequences. This bottom portion is a sequence diagram, actually. So we've got a use case on top of the sequence mixed in. Another variation of UML. What this is. It just basically provides you with a little bit different abstraction about the same concept. So what are we looking at new? 2 next project deliverables, and this is where I show you these project deliverables after this. After you come up with the requirements, we're going to do analysis and redesign. And so it contains models, it also contains the blueprint. So we do the modeling first, and then we take the modeling and return it into the blueprint. So let's take a look, actually. So, what was that, number 3? Oops. I thought I had this open, but I guess I closed it. And then how am I finding out these page numbers? I'm going to this here, and I'm doing this from memory, actually. Design is on 75. Analysis on 47. Oh, I was close. I said 46. So 47 and 75. Oops. Oh, that's 108. No, too far. Where am I now? 90. Too far. Hold on. What I should do is pull these templates out. Ah, here we go. Here's something. I hope it's the analysis. No, this looks like the design document. Let's take a look at the design specification. Hello. And then, actually, no, let me go back and I'll do it in order. Just 20 more pages. Let's see. And the reading is actually good because it will go through all of the different components. A lot of the stuff I'm skipping over, actually. Everything you ever wanted to know about object orientation is in the reading as well, if you're brand new. Ah, here we go. Your next deliverable. So the following is an example of the analysis document. Hello. Started on page 46 of the course notes, if you're going to go back and look at it. And you do not have to do this for next time. Just keep that in mind. But this is going to be what you'll be working on after the next class meeting. What we've got is an introduction section. This is not a formal document, by the way. This is just something that I created. It does not exist in the real world. Don't talk about it in the real world. I think you're crazy. No such thing. We're going to have you repeat from the, and this is where things come into play. As soon as you come up with that requirements doc, you can automatically repeat the beginning. So that introduction becomes your introduction. And what you're doing is you're just describing, you know, what the project is about, what it's supposed to accomplish. And some specific project objectives. Usually the beginning part is not too bad. It's the section 1 is good. You're also looking at not a thorough repeat of your requirements, but a description of your requirements in terms of the major features that you're going to include. So where it says overall requirements description, and I'll go over this again next class. I'll go over this again next time we meet to let you know a little bit more in terms of the expectation. But we're just basically covering the basic overview of the system in Section 1. Section 2, this is where things get interesting. So what we do is we take your requirements. Remember I mentioned something about traceability. So all of the requirements are going into the design, and we have a trace one-to-one kind of ability to follow how the requirements were implemented. So the analysis is based on the requirements. So we take our functional requirements, which you may or may not have divided out your requirements document by functional, non-functional, but you can pretty much go through and see which ones are functional. You're not going to do any of this for non-functional. Can you figure out why? It's not really part of your system. If it's non-functional, it's not critical to the system. Why does it need to be analyzed like that? It's a feature, but it doesn't require, non-functional requirements don't require very much analysis at all. So we're looking at our functional requirements. We're going to come up with an entity relationship and a data flow diagram, which I haven't talked about yet, which we're going to talk about. These are two different types of diagrams. They're very easy. You don't even need Visio for this. You can do it in PowerPoint. Paint. Just draw boxes and connect them together. It's not that big of a deal. But you're going to create one of one type, one of the other type, because you're looking at processes. Down here, we're looking at data. So this would actually turn into your database design and your data usage. This is your processing, your data flow diagram. Kind of like what we looked at a few minutes ago with those flow charts. So you're creating one of each that's going in here. And then you're giving me descriptions of your processes. So it's really not a technical document, the analysis. It's more along the lines of, can you write a description of what this processing is doing? Each one of the processing buttons, what does it mean to register a student? Like so, drop a class or something if you're working with that type of system. And then you're looking at any type of performance, reliability, design specification, component deployment diagrams, and then a small little test plan comes out of that. I may or may not actually have you do the test plan in the analysis, but I'll tell you next class meeting what I mean. So if you're going to work ahead on this, you can probably leave out the test plan for the analysis. Just put it in the design document, or if you do the test plan, you just copy it over to the design. Because what ends up happening is you're building the first draft of your design document. So what you're doing is just giving me pieces. It's not a structured document like the requirement specification. It's just not even a document. But I'm having you put it all together so you can submit it as a whole. Just diagram 1, diagram 2, diagram 3, whatever. In fact, the analysis doesn't ask for any UML at all. It doesn't even get that far. It just looks at entity relationship and data flow. And what you're doing is you're going to create a couple of diagrams is what you're going to do for that. I know that was really quick, but it's just a preview on the deliverable, just to give you your correct expectations if you're thinking about it ahead of time. Don't worry about creating it until in the next 20 days. If you can get your requirements document solid by then, you'll be in good shape.
So we are not supposed to do test plan for analysis document?
No, I'm not going to have you do it, but I'll tell you next time.
Okay.
I'm talking way ahead at this point. The problem with the beginning of this course is half the students haven't registered for it yet. Registration is still going on. So I'm going to have to repeat a lot of stuff. So I say just the requirements in the beginning and then hit you with all of the big stuff next class meeting. Unfortunately, you just arrived and you missed about 5 hours worth of lecture we had this morning. My best advice for you at this point is go back and watch my videos. On bhacker.com, I recorded everything. Go back and take a look. You'll see that I went over the syllabus, went over what we're doing, which at this point you're probably going to be extremely lost in what I'm saying. You're not. But yeah, we're doing a project going through the development lifecycle, and you're going to give me deliverables. One of them is the requirements document. The next one is going to be an analysis, and then we go into the design. And the design is the formal document that you're putting together. We're taking the pieces out of the analysis, and we are creating a formal document out of that. So the requirements was a formal document. Did I miss it? Was it on page, does anyone remember? Oh, here it is right here. Good. So we're creating the first deliverable as a regular old standard software requirements document. Formal. Analysis is not formal. Just give you a couple of diagrams. Put it together, call it the analysis. Design is formal. We're going back to formal. So design's got a structure to it. Now we start seeing the 1.0, the 1.1, the 1.2. And what we're doing is we're going to take the pieces that we did in our analysis. What are these pieces? We got a data flow and entity relationship. We got some process descriptions. We got these pieces of information that we dissected after we functionally decomposed, and I'll talk about that next time as well, system down at smaller parts. Well, we need a system before we can functionally decompose it. And then we're putting it together in a formal design specification. This is the template of the blueprint, the implementation. This we give to the implementers. We hire an outsourced company and we give them this design document. So here you go, filled it. Theoretically, we don't really have to talk to them after that. We should have a meeting, you know, to say, hey, do you understand the design document? Do you have any questions about it? You know, and then I came back, oh, what do you mean by this database? You know, what is this? I've never heard of a database before. Oh, and then you explain databases to them, you know, or whatever. And it's probably not going to be something that trivial, but it might be an algorithm for some encoding, some encryption, something more complicated. And then you discuss anything that they don't understand about it. You make some clarifications. You revise this, and this turns into the contract, which means what you give them here is what you're supposed to get back. You know, but you get it back in the form of source code. It's implemented for you. So this is how to write the source code without writing the source code, which is kind of counterintuitive to a lot of programmers who would just rather write the source code. But no, you're not writing any source code. You're not allowed to write source code for this course. So we have our introduction section just the same way as we had it in all of the other documents we've done so far. We cut and paste it, we use it here. Slight modifications to meet the formats. This is not the, section 1 is not the big deal. It's just a repeat of all the other section 1s we've had. I've used some different categories, you know, statement of scope. This is more designed towards the format of the requirement specification, because this is where we get our traceability. So the design document traces back to the requirements, which means we have our goals or statement of scope. We have software context, major constraints that might exist, stuff like that. That's the writing part, we just fill in the blanks. And then we have section 2.0 called our data design. And you can probably imagine what 3.0 is all about, processing. So data and the data processing is what we're looking at. And so in terms of the data, we have a description of the data structures. We have the internal data structure, the global data structures. We break the system out in terms of the data components, which I haven't really talked about yet. And then we have a database description. This is where you take the entity relationship diagram that you came up with and create your database design. Your database system. You might be wondering, well, what if we don't use a database? You know, 99.9% of all applications out there, if it's a real application, is using some sort of data. And it's not using data. It's not really a system at all. When you think about information systems processing, software in general, it's manipulating data. It's collecting it, archiving it, changing it somehow, creating it. It's doing something with data. So we got the data section. And then in section number 3, this is really our processing section, but it's not called processing. It's called the architectural component level design. If you think about the concept of what our software is doing, it's the design, the components is the processing. It's processing information. It's functioning. It's communicating. We have different components that we all put together, and it creates the system. That's doing our processing. So we're really in section 2, we're actually talking about processing, but we're not calling it that. We're using the lower levels of details in terms of the abstraction. So description of the program architecture is presented. So you might say, oh, this is a client-server program. And here is where we're actually determining that it's going to be written as a client-server program, or it's going to be written as a peer-to-peer program. Or we could leave it out and say, it's a networking program, figure it out. So the more specific, just like the requirements document, the more specific you are with the design, the more constraints you put on the overall implementation. So if you say Visual Basic 6.0 or Visual C++ 6.0, and that's outdated, you're going to build it in 6.0. So So again, unless it has to be built in 6.0, doing it in 6.0. Anyway, so you have a program, structure, architectural design, architecture, alternatives to design, because here's the problem. You haven't built it yet. It's brand new. You got a beautiful set of requirements. You did all your analysis. You understand the system now. And now you see, well, it could be a distributed application. It could not. We thought about it. And here's all of our design alternatives. You don't have to do a full design on the alternatives. So you just basically say, well, I really want it to be a .NET application, I think, and we want it to run in this environment on this architecture, and this is how we want the components brought out. However, if you find it impossible to do it this way, Java's our next bet. Not a good example, but it's kind of a similar something you might be able to relate to. Just different styles, different things that you can do with it. And in the architectural design, and it's really hard to talk about this diagram, this document, because you don't know what these concepts are yet. That's going to be the focus of next class. But and if you read ahead, you'll get a really good understanding of it. What you're looking at in terms of the overall structure of the architecture are components. It's a component level description. So you go out and for each one of the components, you say component number 1, component number 2, which is the component ends. Or you say component server, component client, component peer, component node, node 1, node 2, and you describe each one of the components. And what you're doing is you're looking at the processing narratives of the component. What is the component doing? What is it composed of? And then you have component end processing details and the algorithms. You're not writing any source code, you're just describing. It should do a ordered search or something, or it should use this algorithm or that algorithm. And so, section 2 is the data. Section 3 is the processing and all the different components. Section 4 that comes out of here is the user interface design, the most fun part of the entire application. So, as you've developed your project teams and you're working on your requirements document, you're going to figure out what everybody likes to do. And what I would suggest doing, if you're working as a functional team, divide the work out. So, one person can work on user interface design, the other person can work on the processing, the other person you're the data person, you're this person, you're that person. You break it out, and you separate the components, and you have everybody write different parts of it, you put it all together. That's how a good functional team works. And that's very hard to do. It's almost impossible from a distance, but now modern day telecommunications and email and stuff, you can send files back and forth. You can actually even open up a Google Doc and share it all together. In fact, that's not a bad idea. Use Google Docs for your requirements, for your analysis and stuff. And you can collaboratively work together from a distance, which is actually how stuff is going on these days anyway. Even who works in an office anymore? SharePoint. Yeah, you got so much stuff going on these days. So. For you who came in late, you should get yourself on a team. We already formed some teams in this class. Talk to these guys before you leave. I don't know how many's in what did I put the max at 5? Yeah. So you probably could, swindle your way into one of these teams. Yeah. Okay. Yeah, software engineering 2 is a fun class. This one's totally different. Right. All right, so section 4 is all about the user interface design. And some of this stuff is no-brainer. Some of the stuff is going to need a little bit more explanation, and you're going to get that in the next class meeting. But I'm just trying to give you a preview of the expectations, what to look forward to. Section number 5 is pretty minimal. It's the restrictions, limitations, constraints. Section number 6 is the testing, which you're not going to have to do in the analysis document. So you scratch that testing part off the bottom of it. We're going to put together test cases. That's all you're going to have to do for this entire section, for section 6. If you want to, you can go into some of these other things, performance bounds, identifying issues, identifying pieces that should be testing, and then any tested, and then any appendixes that you might have. You might not have any at all. If you're working with a software program that's going to use some specifications from something, you might have to refer to the spec document or refer to that spec or something. And that's what would go into the appendix area. So I know this was kind of a brief summary of it, and I know some of you, I wanted to go through it fast because I know some of you guys have a class after this. But what we have going on here is just a brief summary of both of those two deliverables. Next time I'm actually going to go through both of them a lot more. Are there any preliminary questions on them? So you guys have a lot of homework, actually. Because what I would do is read through the 160 or so pages, and maybe 113, I think I'm over-exaggerating. 113. Read through the 113, just briefly summarize through. I wouldn't read it word by word, because some of it you're going to know already. Some of it's really bonehead. The business guy in the back, you might find it all interesting, because you don't have a background in it. So you're going to find it, the course notes, you're going to find the most helpful, actually. And it's 113 pages of it, but don't try to read it all. But if you can try to get to a review of most of it, form your teams, put together your requirements document. That's enough for 20 days. And then when we meet again, we're going to, I still have one more lecture, so even though it sounds like I'm wrapping it up, I'm not. Just wrapping up the course notes. This lecture is only 24 slides, don't worry. But yeah, when we meet again, then I'm going to go over the analysis and the design, give you the deliverables, because then you'll be focused on it. Right now, you're probably just focused on getting organized and getting the requirements down. Any questions before I continue with our last lecture for today? No? Still keeping up? Okay, good. Coffee's helping me. All right. Lecture number 4, system modeling in the analysis stage. There's a little bit more examples is what this is. So the last lecture, number 3 that I just showed you, is more along the lines of what is analysis. Here are some typical models. For you who's leaving, we won't have class tomorrow, just today. Okay, just let you know. Because he showed up for like 5 minutes, 10 minutes. He wasn't here earlier. I just thought I'd mention it because if he shows up at 3 o'clock tomorrow, anybody here? Save the trip. I know his time is limited. System models. All right, this is what we're doing. We're modeling the system. And so we have abstract descriptions of the system and whose requirements are to be analyzed, which is really the formal definition of, and the objectives here. And I remember before I said we have different views of abstraction. And we take the car and we look at the inside, the outside, the tires, the engine. What we're doing in the software is we get external, functional, and structural perceptives, showing different levels of detail about the architecture, about the interactions of the system itself. Model weaknesses. One picture, it's kind of like when you get a digital camera and you go on vacation. And you try to capture the moments after you plan this vacation out and the museum was closed. And you had to go back and revise your requirements. And you had everything figured out, and then you start then at the end of the vacation, you take a look at the pictures. You go, oh, what happened to that nice restaurant we went to? We didn't take any pictures there. Wow. Gone from the memory completely. Out of. Oh, what about that person we met? Up, gone. You know. And then you look at the pictures, you go, that was a pretty short vacation. I didn't have that much fun. Or look, this person's not smiling in any of these pictures. Problem with the pictures is it doesn't really represent the full reality of what actually experienced, or what actually you did on this vacation. It's just a snapshot. Well, that's the problem with the models, and one picture is not going to show you the entire vacation. It's only going to show you 5 seconds. I don't know how long it stood there and posed for the picture, but that's about all you get. So they don't model non-functional system requirements. They don't model how you felt that day. They don't model anything about what you ate for breakfast or anything of that nature in terms of the picture. In terms of the system, it's not modeling any of the non-functional stuff. As I mentioned before, it's based on functionality, functional requirements. You're missing everything associated with the non-functional. And they don't usually include information about whether a method is appropriate for a given project, for a given program or scenario. So you don't know whether or not your model is actually right. Just the same way as you don't know if you saw everything in Paris. You may have just seen one city, one small little area, or one street. So you don't know. You covered everything. And they produced too much documentation. Yeah. You know how many slides people showed? It's like you're sick of the vacation pictures after the first 10, 15 of them, and we need to see 200 of them. That's why I don't like Facebook, actually, because there's too many pictures. It's overload. I don't want to see everything. And same thing with software engineering, and the system models are sometimes too detailed and difficult for users to understand. Not the same case with pictures from your trip, but yeah, it could be. What am I looking at? What ocean was that? You know, it may not even be labeled properly. You might be saying, "Oh yeah, we went to California and we saw the Pacific Ocean." Well, that would be correct, but the Atlantic Ocean, California. Okay, that's not right. All right, so systems analysis, the model for data modeling and design. Here is our brief list of the ones. Remember before we talked about UML, and I said we're going to look at 6 or 7 of them. Systems analysis and design, we're only going to look at 1, 2 of them. Not too many, but they're most popular, the ones people always remember. We could go back and look at tons of other ones, but they're all outdated. None of them are being used. The most popular is the entity relationship and the data flow diagram. The concept of the data dictionary, it's not a diagram. It's a repository. And it came out of the concept of case tools. You guys heard of case tools before? No, that's an outdated term. Now we hear about developer studios, developer tools. We don't hear about CASE. CASE stands for computer-aided software engineering. Never got popular. Nobody ever said case this, case that. Now, if you say, even people don't even know what an IDE is, Integrated Development Environment. But the acronyms seem to get lost. But anyway, long story short, Case tool was an automated way of building software. It integrated the models, and it created what was called a repository, which kind of sounds a little weird. But so people changed it to data dictionary, something that they could pronounce or understand. It's a dictionary of all the data. Well, it's kind of like the UML stuff these days in object-oriented design. We have our data components and keep track of those because we share the information between the objects. Same concept. We just keep a dictionary of all the data that's being shared, which is not really a model, not a diagram that we put together, but those are the data descriptions, the process descriptions that you're putting into your design, your overall design. And then we have object models. And many of these models, there's a blurred distinction between the analysis and the design. Are we analyzing it or are we designing it? Is what the issue is. And the concept of going through the analysis creates the design. In theory, you're doing both analysis and design together. We have different data types, as I mentioned before. We have the data processing, the composition model, the architectural models, classification models, response models. You don't have to memorize any of this stuff, actually. It's just giving you a little bit of background information on the different types of models. And the next kind of slides, it goes through some different model representations. Context models, as I mentioned already, are used to illustrate the boundaries of the system. Concerns with making decisions about position of the system boundaries. Where does this system end, the other one begin? Architectural models show the system in relationship with other systems in terms of its architect. Here's a contextual model of an ATM machine. So we have the auto teller system, and then we have all of the other components. You see, it's not really a complicated diagram. In fact, it's fairly simple. This is what you're drawing for your analysis, which means, you don't need Visio for this. You could do it with Paint if you wanted to. Process models, it's going to be your data flow diagram. And you're looking at the overall processing of the system that's supported by the system. The data flow models are used to show this, as we've seen before. Here's a data flow diagram. This is what you're going to be creating. And next time we're going to actually build some of these diagrams. Excuse me, some of these models for you. And you're modeling your system. This is your system that you're doing for your project. Fortunately for you, you don't have to model any other system, which is great. Other classes you take that don't work with one centralized thing project. 5 data models of this. You just start creating models and stuff. It's just that you can't put all the pieces together too well, but It's great practice for creating models. But who makes a living creating models these days? Nobody. Make better living creating software, I would think so. So this is the data flow diagram. We're using the data itself, the processing through the system, simplified notation for customers to understand. Actually, a lot of these diagrams, easy for customer to understand. You don't need an engineering background. In fact, a lot of customers look at these things and go, oh, I know how to, oh yeah, that's right. In terms of the model itself, you're looking at the functional perspective, as I mentioned before, non-functional functional requirements. And you're looking at tracking and documenting how the data is associated with each one of the processes. The diagram is used to show the data exchange between the systems and the subcomponents, and how the system is working in the context of the other systems. And our data dictionary, by definition, is the list of all the names used in the system models, descriptions of the entities, the relationships, the attributes. I haven't really explained entities, relationships, and attributes yet. That's part of the entity relationship diagram. Are you guys familiar with these types of diagrams, right? I got some yeses and I got some no's. You are. People in the background. Oh, you are.
That's the
Oracle. Yeah, that's the one advantage you have from taking the database class first. When you model the database in your system, you already know about entity relationship. You're building a database. You're building a model for it. So you already know about entity relationship. Actually, I would say that's probably one of the advantages for taking multiple classes from the same instructor. You get the same methodology going through, but you see all different perspectives of it. So from the Oracle class, we learned how to create databases. Software engineering class, you got to design the database, which means you got to use the same model. So if you were a database person, you'd work in a software engineering house designing models for the databases. And that's how the pieces fit together. Data dictionaries. Doesn't relate to anything nowadays. It's a repository, dictionary of information, glossary of terms. Object model. We will spend a good 2 or 3 lectures on UML next time. What we're going to look at is the object descriptions of the system in terms of its object classes. So the object is the class if you're brand into the concept. And don't panic if you don't know anything about object orientation. You don't have to understand the modeling. The modeling is actually quite straightforward. You're not actually programming it, you're modeling it. So what we'll be looking at is the modeling structure, which is really simple compared to the programming. Natural way reflects real world. In fact, people like the object-oriented design methodologies because it sort of resembles the real world in a lot of ways. If you can resemble the real world in programming, I don't know if it's possible, but if you can, this is the closest people have gotten to it, I think. More abstract entities are more difficult to model using this approach. Structures the system as a loosely coupled objects with well-defined interfaces, theoretically. These are just some points about object models. You can certainly download this slide set and read through each one of the slides at a slower pace. But just to give you an orientation to it, here's an example of the object model. Again, it's nothing more complicated. Actually, this is really a class model versus an object model. It could borderline on a class model. The reason, actually, the quick way of telling is how many boxes you have nested. You see in the middle here, when we have the 3 sections, that's a class, not really a model. I mean, not really an object. Object wouldn't have it broken out into identity, states, and behaviors. So we got the identity, the state, behavior. I'll go over all this stuff next time, but that's an example of what you have to look forward to. And then our entity relationship model. For those of you who haven't seen it yet, it's used for model databases. And it's a tool for displaying and manipulating entity diagrams for databases and data storage. Not used just for databases. It can be used for any type of data archiving, data storage. And we have some unique symbols that are used with it. And we put it together. Here's an example of an entity relationship diagram where we have identified entities and we are showing their relationships. These diamond symbols are the relationships. The rectangles are the entities. So we have entities and relationships and connect the dots. Actually, just out of curiosity, well, only one person here is from returning. No, you weren't the back. Did you take the Oracle? How many people have taken the Oracle class?
Me?
Did you take the Oracle class?
No,
Only one person in here is taking the Oracle class.
I was in software too.
Okay. Well, I didn't cover entity relationship those in my class. Importance of modeling. A little summary going on here. It's a simplification of reality. Yeah, that's why we do modeling. That's why we write process schedules and stuff. And it helps us understand the world. It's complex. It breaks everything down into a model. And we build models so that we can better understand the system that we're developing. And the more complex the system is, we cannot comprehend each system in its entirely, so we break it out. It's a level of abstraction as well. So creating the model helps us divide out the system components to logical units. And models can be formal and informal. And the more complex the project, the more valuable the models become. Then you can take the model and actually understand what it is you're building, hopefully. And the choice of the models. Well, as you've seen so far, I kind of previewed through a lot of different models. Depends on the problem you're solving as to what set of models you're going to use. For your design and your design document and all the analysis that you're going to do, I'm going to tell you. I'm saying one of these, one of those, and one of those. Okay. You put one in each of each type. In a real-world scenario, you pick the models that are appropriate, which is why people like UML. So model for anything and everything. So you just, I'm doing a network one, so you pick a network diagram model to use. And so you have a larger selection to choose from, which is why people like it for some reason. But also it gives you more variety. And if it's going to be implemented in object orientation, you might as well model it that way. So it makes sense. It's more pure to the programming. But theoretically, when you're creating your design and your models, you're not thinking about a programming language. You're not supposed to be thinking about a programming methodology at all. What you're doing is you're modeling the system. You're not modeling the programming. So you take the model of the system and you implement it. That's why they call it implementation instead of coding or programming. People like to use the word implementation because it's not source code writing. It entails a bit of source code writing, but you're creating a database as well. You're writing the source code, but you're selecting. If you leave the implementer up to the implementers to select the language, they'll do a better job. So if you go in the design document, you write the source code in C++, and you tell them, here's the design, and it's already written for you practically. It may not necessarily be the best implementation. If you leave it open, don't give them any source code. Just tell them, here's the system, here's the models of the system, here's the design, here's what the system processing is doing, this is what the data looks like, here's all the requirements. Have at it. They'll pick the best language, they'll pick the best environment, and build a better design. Yeah?
Normally, a system analyst is responsible for the design.
Yep. We have systems analysis, you missed the beginning, systems analysis and design, where it's actually broken out into two separate stages. We have analysis that leads into the design. If you look at the video, you'll that's the first thing I started out with. All right, that's the problem when you come in a little later. It's like, oh yeah, I got it. You talked about that already.
I was not doing that on my side.
Oh, it's okay. I'm not trying to give you a hard time.
Not miss the part.
Don't worry about it. You can see we had more people before lunch too. It's the ITU illness that goes on here at lunchtime. The siesta. Actually, in Mexico, they call it the siesta. It goes from lunch till about 4 o'clock in the afternoon. 3 o'clock in the afternoon. Yeah. Every model can be expressed at different levels of precision. The best models are connected to reality, hopefully. These are some concluding thoughts. No single model is sufficient. That's why we have several different models, and every non-trivial system is best approached through a small set of nearly independent models. So keep it independent. Don't make it specific towards any language or any methodology. So it's kind of like the requirements document where I said, outline everything you want, but don't be specific. You're doing the same thing with the analysis and also with the design document. You're creating something that can be designed this year and next year, the following year, because this is going to grow with the company. If you're a software development company, hopefully you're going to be in business for more than one project, hopefully. So you're going to try and reuse everything. And the more you do this, the better you get at it, and the more you can reuse from previous projects. You're not reusing the concept, But the modeling techniques, the format, the methodologies that you're going through for the analysis that leads to the design, you're learning how to analyze and design. You become a stronger team, you become more proficient at it through practice, which is why you never hire a brand new software engineering company. You don't look like you've been in business for like 10 or 15 years. Because then you're competent at least. Can't just graduate from school and become a competent software engineer. You can forget this here. We already talked about your topic and we already talked about your requirements doc. So, and you don't have to print it out for the next class, as that slide said. You can, and it's not a graded assignment, your project topic. You can upload it into the EMS. So. All right, so, oh, good. Target time was achieved, 3:05. I say between 3 and 3:30 is what I promised. Questions, comments, and concerns before I leave you?
Do we have these slides?
You do. You have them, and that's an excellent question. They are right here. You go into summer 2011, and you go here, software engineering weekday and weekend sections. And during the lunch break, I put the videos up here, actually, the first two from this morning. But over here in the lectures, you've got all the PowerPoints. We just went through number 1 through 4. Yeah, 4. 5 starts in, I believe, with entity relationship diagramming. Next time we're going to actually go through 5. Well, there's only about 20 slides here. I'm going to, well, because I don't have to spend half the morning going over the syllabus and requirements and everything. You guys will be, and you'll have your requirements ready, hopefully, so you'll be ready to take that and start doing your analysis and your design. But nothing is officially due until the very last day of class. So you can procrastinate, wait until the very last week. And then you'll have to end up fighting the tech support people to get through because the system will be down because every other student will be trying to access it simultaneously. And they won't be able to handle the system load. That's what happened actually a couple weeks ago, last week. Any other good questions or bad questions or questions in general? The EMS is not actually built yet, and we don't have any assignments for this course. We have one huge project that's 55% of your course grade. We have a midterm exam, and we have a final exam, and we have a CSLO essay, your favorite.
I'm kind of familiar with it.
Yeah, I know. You've taken more classes. You've taken classes already. So you have 90% of it down. If I were you, I'd go through and just take a look at the syllabus that's in here. If you take a look at the, and this is the other thing that's kind of new to this class, not to any of my other ones, is I actually have this link here for course notes, which is that 113-page document I've been talking about. So. And the next class meeting, I believe, is going to be on the schedule that I have right here, which is June 18th, which is, considering today's the 21st, less than a month ago, less than a month away. So I think I've given you more than enough work to do between now and next 20 days, which will fly by quickly, actually. And you know we don't have class tomorrow. Would you guys prefer to have it stretched out instead of going till 3 o'clock? No? I like the one. I only like it because people like to travel. If you're working and you need to have a day to travel to get back, you could take Friday off, you know, and then travel down here, come here Saturday and come back Sunday. Or I guess the extreme person. I've seen this before during the final exams. They come in with the suitcases. They fly in the morning with the, sometimes they don't even have a suitcase. They just have a backpack. They come in. They look like they've been on an airplane all night. They take the exam, and then they get back on the airplane and they go back to sleep. And then they make it back home.
That's what happens.
That's what happens. Sometimes they come in and they look like they've been sleeping on an airplane and their hair's all messed up and they got, you know, or they're carrying the luggage with them. It's like they got everything with them because after they leave here, they're going somewhere else on a business trip. This is just a pit stop. All right, well, I'm going to end the video then because we don't need to record everything else here.